I'm going to talk about basics of experimental phasing. There will be 2 more lectures which deal with experimental phasing, one about anomalous map and one of advanced ShellXC CDE usage. So this lecture will merely form some basics and some concepts. On the other hand, you are possibly one of the most expert audiences in experimental phasing I have been talking in front. So you can find the slides on my homepage if you want them. Most lectures are mirrored as Ruby. And yeah, the list we already had. Now, the first question is, what is experimental phasing? Now, a few years back, I did a survey in Randy Reed's lab. And I went around and asked everyone about what is experimental phasing. And I think the best answer I got was from the PhD student in his first year who said, experimental phasing is what you do if MR doesn't work. That's often true. Experimental phasing methods depend on intensity differences. These differences can come from different effects, but all experimental phasing methods depend on intensity differences. These differences are caused by a marker atom substructure, referred to as the substructure, the heavy atoms, the markers, whatever. These are of certain elements. MAD and SAT methods exploit the anomalous signal from one or more data sets of the same crystal. SIR and MIR methods use the difference in reflections between crystals that have incorporated or not incorporated a heavy atom species. So they are often called soaked derivative crystals because they're derivative of the original crystal. And the crystals have to be isomorphous to be utilized. So this is basically the list of experimental phasing methods that are in use. SAT, with the special case of sulfur SAT, which exploits the native sulfur. MAD, SIR, of which a special case is RIP, radiation damage-induced phasing, MIR, and then combination methods between them. Now, you can do most, if not all, of these at Diamond, which brings me here in a way. But first, let's talk about some basics. So for some of you, this might be things you know, but I like to start at the very, very fundamentals. So for every reflection, there is a structure factor, FHKL. HKL tells me where in the reciprocal lattice it is. If I know all the structure factors, including the phases, for my structure, I can calculate the electron density map and hence also fit a model into it and get the structure. Between the structure factors and the electron density, we can translate by using Fourier transform and Fourier synthesis. Now, structure factors can be regarded as a wave. That wave would have an amplitude. We call this amplitude the absolute of FHKL, and a phase, which we call phi HKL. They can also be seen as a complex number. So we have got a complex plane with the imaginary and the real axis, and then the structure factor is a vector, which has a length, the amplitude, and an angle over the real axis, which is the phase angle. Now, we can get the amplitude of every structure factor for which we have measured a reflection because its squared is proportional to the intensity, how black the reflection is. However, the phase cannot be measured directly. And this brings us to the central problem of all crystallographic data processing, for single crystals at least, the phase problem. Now, anomalous scattering. This talk will follow us through with a little bit of MAD on a SAT case. Things for SIR and MIR are similar, but we have to follow one method through. So anomalous scattering. Each structure factor, each FHKL, has contributions from each atom in the unit cell. So each reflection sees every atom in the unit cell, and every atom influences all structure factors. Now, every atom gives a contribution, small f, HKL actually, And then if we sum them all up, we get our structure factor. Now, there is Friedel's law, which tells you that in reciprocal space, two reflections that are centrosymmetric to each other, the so-called Friedel pair, have the same amplitude. They have the same absolute of FHKL, or the same length on the imaginary plane. So this is the structure factor of one reflection, and that's the Friedel mate, and they have the same length. And they have opposite angles, as you can see. Now, for a long time, people thought this is true, although they observed deviations from it, and they thought these deviations are systematic errors. This was the early days of crystallography. All measurement was done by someone looking at a reflection, comparing it to a charge, and saying it has this intensity. Until a man named Byfoot came along. And Byfoot saw there was a systematic way to these deviations, and that actually Friedel's law is not universally true, but it is broken. Actually, we know today it is always broken, but most often to such a little extent that we don't notice it. And that is because the atomic contribution does not only contain F0, which depends solely on the resolution and the element, but it also has anomalous scattering, which has a real and an imaginary component named F prime and F double prime. These are observable near the absorption edge of the atom's element in question, and hence they are wavelength dependent. So anomalous scattering can be observed at certain wavelengths of X-rays, and not at others because the effect is too small. Now here you can see lambda in one direction, energy in the other, and contributions over an edge for F prime and F double prime. So you see that F double prime goes up, peaks, and then slowly seems to get down again, while F prime just goes down and goes back to what it was. If you want to know these plots for your element, and you know at which wavelengths you should measure to have anomalous scattering, I recommend this server of Ethan Merritt's, where you can just give the element type and get this plot. Now, the F double prime contribution breaks Friedel's law. And that is because all of the F prime contributions from all atoms are added most often backwards. So they make the FHKL smaller. But then F double prime is added at a 90-degree angle to this. And the two resulting vectors are not only different in their phase angle, it's not phi equals minus phi minus h minus k minus l, but also their length has changed. So the length, which we measure in the form of the intensity of the reflection, is now different. And we can exploit this for phasing to determine the positions of these elements that give us this effect, and then from the substructure to expand to the phases of all of the structure. At least we hope so. So how do we find the substructure exploiting this effect? Now, phases of strong reflections are related. The phases are not random. There are certain things in electron density that make the phases obey certain rules. For example, electron density is always zero or positive. Right? You cannot have negative electron density. You also usually cannot have two atoms on top of each other if they're full occupancy. So these general rules to electron density give rise to certain rules about the phases, which are harnessed in the form of the triplet and Sayre equations. These relationships between phases of different reflections, once you know the phase of one reflection, are relatively easy to resolve for a few atoms. giving rise to direct methods, which is a popular small molecule phasing method, where they only have 100 atoms. They can use direct methods just as it is on their data without using any experimental phasing at all. It's ab initio phasing. They just get the atomic positions out. And another thing that's very important to the substructure search is the usage of normalized structure factors, so-called E-values. E-values are the structure factor amplitudes divided by the average structure factor amplitude in that resolution, basically. So if this refers to a structure that has, atoms that can move and that have a B factor, this should refer to point scatterer atoms. And this is of the essence for macromolecular experimental phasing, because actually the moving about of atoms makes them very hard to find. So generally, we are borrowing the direct methods that I just mentioned, as well as Paterson methods from small molecule crystallography. I'm not going to talk so much today about Paterson method because it's going to play a role in the next lecture, where we talk about anomalous maps and anomalous Paterson maps. But let me just say this. Paterson methods give you the vectors between atoms in a structure of relatively few atoms, and are also used in small molecule crystallography in a very old-fashioned way to resolve your small molecule structure. And both of these methods require separate atomic electron densities to locate the atoms. Now, this is a problem, isn't it? Separate electron densities. If you think about the last electron density map you saw for a protein, most likely the atoms weren't separated from each other. They are fused in one large blob that vaguely has helix or beta fold shape. Now, so this means we can't use direct methods or Paterson as they are for small molecule crystallography in macromolecular crystallography. However, if we generate a map only from intensity differences, so instead, and I will go into this later, if we take, instead of the intensities we measured, the differences that have been caused, for example, by anomalous scattering, which also all have an HKL, we get something that refers only to the positions of the atoms that cause this effect. I will cover this in great depth next week. But for now, let's say the marker atoms have large distances usually, and the anomalous signal only corresponds to them, and hence we can borrow these methods to find the positions of the substructure. Disulfides. They are pretty close, aren't they? I'm not sure. Are you still awake? Yeah. It's like, you can interrupt me with questions, by the way. Please feel free to interrupt me with questions. And also raise your hand and say, Andrea, this is boring. Please move a little bit. Or can you please go back 2 slides, because I really didn't get what was in that slide. Just do that. Interact with me. Disulfide becomes supersulfurs. So when you hear the expression supersulfurs, that usually means disulfides. They are so close to each other, they fuse in 1 to blob at most resolutions we are using. We use Paterson seeding, which gives us a starting point, certain conditions for the starting phases for certain reflections. And then we use dual-space direct methods to expand the phases we knew for a few reflections to all of the reflections. And we then go back to real space where we change things a little, which leads to a much faster convergence. But I want you to be familiar with these 2 terms. Paterson seeding means we start at information from the Paterson map, about which I will talk next week. And dual-space direct methods are direct methods that both work in reciprocal and in real space and exploit the fact that phases of different reflections are connected. Now, substructure search, yes? Yes?
In small molecule crystallography, nowadays, most structures are solved by charge flipping. Is that in P1? So is that something which has been really tried now for macromolecular crystallography substructures?
To my knowledge, this has not been extensively tried, although in ShellXC, we are using something very similar to charge flipping, but that is at the density modification stage when we already know the substructure. There are some good reasons why it should be very difficult. Most of them having to do with only having low resolution data available, which makes it extremely difficult to actually find the substructure in such ways. But I don't know of someone actually trying this. Why is this an overdetermined problem with noisy data? How many, what is the answer we want? What do we hope to find in substructure search?
Locations.
Yes, the substructure locations, the positions of the atoms. So we are searching for 5 atoms. They have X, Y, and Z. So we have 15 numbers we are searching for. And how much data do we have? Well, we have supposedly thousands of anomalous differences because every Friedel pair gives us an anomalous difference. And even once we have taken symmetry into account, we may still be left with hundreds, if not thousands, of differences. So we have a lot of data to find very few numbers. And that brings with it problems because these data are so incredibly noisy. You can imagine that the anomalous difference is perhaps 1% of your intensity. Now, if your background noise is 2% of your intensity, you're already into trouble because you will not find it. You need to measure data that are pristine, that are not containing much error, meaning that the multiplicity needs to be high. You need to measure every reflection a few times. You also want to maximize the anomalous signal, which is something that I-23 people are hopefully, certainly very good at. But it is important to remark that the resolution range highly affects the outcome. The farther out you get, the higher your resolution becomes, the weaker your reflections become. And that means the influence of the background is stronger, right? The weaker your reflection, the higher its sigma, the more difficult to determine its intensity exactly. The anomalous signal is a percentage of the intensity. So certainly your high resolution range where your crystal stops scattering doesn't contain any anomalous signal of note. You want to actually cut your data back to where you can still extract the anomalous signal with some confidence. You need good data quality. Intensity outliers are very problematic. So on a conference a few years back, I was presented with a structure that was unsolvable and only solved when half of the data set was deleted. What had happened is the beam stop mask was not exact. One of the low-resolution reflections, which have major influence in direct methods because they're very strong, they're absolutely used for direct methods, was obscured half by the beam stop in one of the images. If that image was kicked out, the structure would solve. If it was left in, if this was integrated, it gave rise to a huge anomalous difference. Because this reflection was partly overshadowed, it had way too low intensity compared to its Friedel mate, giving rise to a huge anomalous difference. And the effect of it all was the structure could not be solved in a million trials. So it's important to look at masks and to do proper data processing. Scaling, in particular anisotropic scaling, is also needed and applied by, I think, today almost every experimental phasing problem. However, even if we have found the substructure, we have not resolved the handedness of the substructure. I hope you're all familiar with the term handedness. We don't know which enantiomer we have, basically. But we have density modification, which will do that for us later. Now, imagine we have found the substructure with dual space direct methods. We know the positions of the atoms of the substructure, at least to a certain degree of certainty. We want to phase the rest using ShellXC. So we can combine all the contributions with atoms that were marker atoms and all the atoms that were not marker atoms calling them FA and FP respectively. So that would look like this. We would have all the contributions from the protein and all the contributions from the anomalous scattering, and we add them up, and we end with the total structure factor. Between them, there is an angle, actually between FA and FT, and we call this angle alpha. Now, if we know the substructure, we can calculate this very vector because we know the phase and the amplitude that we expect for our substructure. Now, if we turn this around, alpha is phi t minus phi a, we get phi a, which we know, plus alpha is the phase of the entire structure factor. So if we find a way to get this alpha, or at least estimate it, we can calculate the phase of the entire reflection. How do we get it? So one way to get it formally is the phasing equations. That's also only true if we have no errors. And I know it looks rather complicated, but let's have a closer look. There's A, B, and C. They depend on F prime and F double prime, and hence on the wavelength. There's Ft, which is the total structure, and Fa, which is the marker substructure, marker atom structure factor. And we know that alpha is phi t minus phi a. Now, for each wavelength we measured, only one if we've measured SAT, but we now imagine we have done a MAT experiment, we've measured several wavelengths. We have different A, B, and C, and we have two observations, the two reflections. Fa, so the length of Fa, the length of Ft, and alpha are the unknowns. So given good data from at least two wavelengths, having 4 data and 3 unknowns, we could solve the equations, and that would be MAT then. And it would work best if F prime and F double prime differences were very large. In SAT, however, we have only 2 observables and we've got 3 unknowns, and that poses us with a problem. So we do a few assumptions which are only very vaguely true, and I'll show you this to you graphically in a moment. And amazingly enough, even if we make the assumption that F total would be like, the average of the 2 Friedel mates, and this is sufficient to estimate alpha to start density modification. Now, graphically, and this will be, by the way, the most complicated 5 minutes of this talk. So from about, in 5 minutes, it's downhill, and we can, relax. You remember we had that, so FP and FA give F total. Then we have all the F prime contributions and all the F double prime contributions added at a 90-degree angle, giving rise to, the total FHKL. Right. Between these two is the angle alpha. This is all things we have just covered. Now, imagine we have measured 2 reflections. FHKL and F minus H minus K minus L. We don't know their phases, so we only know they lie on somewhere of these lines. We know also that FHKL is much larger, clearly, right? This radius is much larger. Now, looking at this, we can say that the F double prime contribution, which makes the 2 amplitudes different, must be pointing backwards for F minus H minus K minus L, and must be approximately pointing in the direction of FHKL for FHKL. And this means that for FHKL, alpha must be approximately 90 degrees, and this is very approximate. So again, F double prime contributions have to point in the same direction as FHKL if FHKL is a much darker reflection, much higher intensity than F minus H minus K minus L. And F double prime has to point in the opposite direction, hence making F minus H minus K minus L smaller. So we can estimate alpha for this type of reflections. Then there's, of course, the other one, which I'm not drawing because it's very similar, and that is when f minus h minus k minus l is much larger than f h k l. Hence, alpha must be close to 270 degrees. So we know that the reflections with the largest anomalous differences must be alpha equals 90 degrees or alpha equals 270 degrees. As you can see, this estimation is incredibly rough, right? It could be 100 or 110 degrees instead of 90. We would never know. It always amazes me that this works, because just from this is much larger than that to say it's 90 degrees. There is, however, one more case for strong reflections that we haven't talked about. Can anyone think which one that would be? So we've got three cases. One is FHKL being larger. One is F minus H minus K minus L being larger. Yes, exactly. So they're the same or very similar. What has happened here? Well, either the F double prime contribution is really small, or it's almost perpendicular to the structure factor, in which case it wouldn't raise one of them very much. So in this case, alpha must be close to 0 or 180 degrees. We don't know which one, and that gives this we can't resolve here. We need to resolve this with density modification. We do not know that. If you use ShellX and you look in a file that's called something underscore fa.hkl, you will find 90 or 270 degrees values as the last column, which is exactly the alpha angle. Now, having done this for the strong reflections with large anomalous differences, we can now calculate the total phase, the so-called initial phase after substructure determination. And via Fourier synthesis, we can get an initial map. We want to do this twice because we don't know our handedness yet, once for the substructure and once for the mirrored substructure. We use also sim weights and sigma A coefficients to improve the map, but most importantly, we now need to apply density modification. Density modification in ShellXC is a little bit different from other density modification, but let's talk about the concept first. Now, it is based on areas filled by disordered solvent. The solvent area is flattened or flipped. NCS averaging can improve the map quality, and high solvent contents gives often better improvement. Let's go back to the first thing. Disordered solvent area. So we have the protein in parts of the crystal. Proteins are large and they don't pack well, which usually means there are spaces between them. These spaces are not empty. They're usually filled by something that is not quite as ordered as the rest. Very often, water, glycerol, ions. Soup would be a good comparison. Actually, you will find that a grant I got was named Soup in My Crystal for that very exact reason. How do you think the electron density of the disordered solvent region differs from the electron density of the protein?
You're only going to have one copy of them, or a couple of copies in the disordered solvent. So the statistical probability of having a water molecule in the same place in the disordered is much lower than that where it's associated with the protein molecule.
Yes, exactly. And what would that mean for the electron density?
Stronger signal.
No, the disordered region has a weaker signal.
So that's what I'm saying.
Yeah, very exactly. The protein has peaks and troughs in its electron density because the atoms are repeated always at the same position. The disordered solvent is pretty disordered, and hence the electron density is flat. Or we like to say it's flat. It's actually not, but it's almost flat. We settle for that. So the electron density of the disordered solvent area and the electron density of the ordered macromolecule are, physiologically different, and we can exploit this, and we do so in density modification. But first, we need to identify what is actually in the new electron density map we've just calculated from the newly gained phases. What is actually the solvent region? And most programs use a mask. ShellXC uses a sphere of influence method, which is working like this. So we've got the newly generated electron density, and we forget for a moment about our substructure. We just take a random peak position somewhere in the map, just somewhere, and we ask, is this an atomic position? Is this a position in the ordered macromolecule or not? We draw a 2.42 angstrom sphere around it. Anyone can tell me why 2.42 angstrom? There's a very good reason for it. No, hydrogen bonds are larger, almost. You need to talk louder. I take wrong answers. I mean, really, I wouldn't, you wouldn't be in this room if I would not hopefully tell you some new stuff. But you need to speak up. So 2.42, ideas. Carbon bond length is shorter, almost. Yes, 1-3 distances between atoms and macromolecules average out at something like 2.42. So 1-3 meaning like first atom, second atom, third atom. Most of them average out at 2.42. So if this peak was an atomic position, somewhere on that sphere's surface lies another atom, if we are in the macromolecule. So we plot the electron density on the surface of the sphere, and we look how much it varies. It doesn't vary very much. We flip the density, land at the original electron density, which will give us 0 in the long run. So we flatten it. It varies a lot because there are 1, 2, 3 atoms on the surface of the sphere. We think we are in the protein. We sharpen the density, and when we add the original map, we still have some sharpening. If we do this for a number of cycles, typically 20, one of the two maps, remember we had one for each hand, looks like protein. The other one looks a lot more rect. And then we can also say from this which one was the right hand. There are also some indicators that help us doing that. After density modification, the structure is solved, and you can start refining or auto-building. Experimental phasing has led to the initial phases, and from there you can go on. I am not going to talk about ShellXC autotracing because I will talk about this in not the next lecture, but the lecture afterwards, rather extensively. Practicalities. So this will be, for everyone who's working on a beamline, possibly not news. High multiplicity is good. Radiation damage is often bad because, those anomalous scatterers, it's not called absorption edge for nothing. They actually absorb a lot of energy, so they're a little bit more prone to radiation damage than all the other atoms. Near the absorption edge, the crystal, I just said that, a fluorescence scan is a useful thing, and you want one. Good low-resolution completeness is paramount because the direct methods really depend on low-resolution completeness, so your phase extension can work properly, and also the low-resolution reflections are the strongest, giving you the most accurate anomalous differences. This is now my personal opinion. I'm very happy after this lecture to discuss this a little bit because I know at least one other good opinion you can have in this matter, which is very justified as well. So please regard this as more like my personal opinion. A collected peak, at least multiplicity equals 4. Peak is here, where F double prime is maximal. Then you have radiation damage? Stop. Try SAT. Use a second crystal to collect the high energy remote. If you have a second crystal, otherwise you have to do with SAT. The high energy remote is here, where F double prime has not much slope, and F prime has been back to what it was before you reached the absorption edge. The last data set should be inflection, in my opinion. And that is because if you had any radiation damage by this time, remember F prime contributions point backwards from what the structure factor would be without the anomalous scattering. So if you had radiation damage, it means likely your structure factor has become shorter. F prime goes backwards. So you kind of artificially maximized F prime by your radiation damage in some way. So I would argue that for inflection point, radiation damage makes the least problems. However, there are people who think differently, and absolutely there are good points against this. At a higher resolution data set, if you still have crystals after this, with a lower redundancy may prove useful for density modification. Because density modification uses all your data and doesn't care so much for the anomalous differences, and their higher resolution can make all the difference in the world. So 0.2 angstroms more resolution makes a lot of difference to density modification. The general data quality should be good, multiplicity completeness, RPIM. If scaling was applied, statistics needs to be checked. So I am getting, very often people come to me when they have experimental phasing problems. About 50 to 60% I send back to integration and scaling. Because their problem was not with phasing, their problem was with data processing. Check the mask, as seen from the example I gave. Inner shell completeness, good. Dataset files well distinguishable. Yeah, at peak and inflection point these days, and at Diamond it's not a problem anymore. But misnamed files from older users are, once inflection point and peak got mixed up, there's no way anymore to solve a structure with MAT. There are, by the way, extra commands for this in ShellX, which I will mention in the lecture after the next. If you ever made a fluorescent scan, keep it, even if it's on a mobile photo. Or if you're a Diamond user, you're of course lucky and you can go on I/B and see it all. If there's an anomalous signal in the collected data, well, you want to know this, right? Because if there's no anomalous signal, what are you doing? But how to know this? So you can look at CC anom. You can look at D double prime over sigma or D prime over sigma. Or you can look at the anomalous correlation of several data sets if you're doing, for example, MAT, or you're measuring several crystals for a set experiment with multi-crystal averaging. You want to know, before you start using the software, what's the space group and do you have twinning? If there are several space groups, you need things that are processed in all the space groups that come into question. If you do SIR and MIR, you also want to have an idea about isomorphism, which you can, for example, see from CC values or a little bit pedestrian from unit cell constants. How many marker atoms do you expect? So if you soaked your crystal with something like iodine, there are certain rules of thumb. If you are doing sulfur set, you should just count the amount of sulfurs you expect in your protein and multiply it by the number of proteins you expect in your asymmetric unit. Which elements or molecules do you expect in your substructure? Certainly, if you've soaked with tantal bromide, you're not going to go searching for sulfurs, or so you hope. What could be the best resolution cutoff? This is sometimes a tricky question to answer. ShellXC, however, does not have an elaborate algorithm to do this. I have often been told it does by numerous beamline scientists and important people, but ShellXC just takes your native resolution at 0.5. So if you've got 2.1 angstrom data, 2.6 will be where it cuts the data. It works in many cases, but better look at the data and cut yourself. Yep.
Low resolution is important.
Yes.
When do you cut it? So
cut low resolution.
Yes,
if I've done my processing, my integration and scaling properly, and I'm confident that my mask was right, I don't cut it at all, meaning I leave a value of 999 in ShellX, and in scaling, don't give a low resolution limit.
many people tend to sort of cut it at 30 because that takes them out of problems, it sort of gives them a nice cycle around. They're not having issues with mass. But often then there's 120 Armstrong, 300 Armstrong spots there. And often they miss out and they never actually what they have.
Yeah. It's indeed true. I end up reprocessing a lot of data I get handed as problem cases, or at least telling them to take the low resolution limits off. It's quite true. Could any marker atoms fuse into bigger blobs? If you're using tantal bromide, if you're having disulfide bridges, at the resolution cutoff you used for anomalous phasing? Could I have fused? Do you want to merge data from different crystals or runs? This is very important for SAT. It can make all the difference whether you have several crystals and you can merge the data. This will hopefully reduce your noise, but you need to be sure it's a good thing to do in your case. And what is your expected solvent content and residue numbers per asymmetric unit? And if you're using ShellXC, the data flow is like this. ShellXC calculates or estimates in SAT your alpha angle. Does the data analysis, gives you some information to decide where to cut the anomalous signal, and does the file preparation. So, for example, it can read in experimental data from XDS or SCAR files, but it cannot read indirectly MTZ files you need to convert. ShellXD does the substructure search, originally being a program for phasing small molecules. ShellXE does the density modification and also the auto tracing I'm going to talk about. Anoda, which I'm talking about next lecture, can be used for validation. All of this is easy to pipeline, which is very often done. So there are, I count, about 19 pipelines for ShellX at least. Some of the more well-known are HKL2Map, the new CCP4I2, but there are numerous ones, which is also why the tutorial that is basically attached to this lecture, I'll talk about it in the end, is using the command line. Because when you can use the command line, you can understand each and every ShellX GUI in the world. So it's a little bit old-fashioned, but hopefully it will equip you, if you want to do the tutorial, to be able to use every ShellX GUI. If your substructure search or other things don't work, you should consider using different experimental phasing programs. ShellX is not a likelihood program. Programs like SHARP or Phaser EP for SAT are sometimes improving your substructure, making just the difference between a structure you can't phase and a structure you can phase. So ShellX is not the only software out there. There's a lot of useful things also for density modification. You've got Buccaneer and Solve Resolve, and you can find a list on the CCP4 wiki. So I would really recommend to familiarize with more programs. So to summarize, experimental phasing methods use marker atom substructures of certain elements to solve the phase problem via the phasing equations. Paterson maps can help. MAT and SAT exploit the anomalous signal from one or more data sets from the same crystal. SIR and MIR utilize several heavy atom soaked derivative crystals, but the crystals have to be isomorphous. Experimental phase solutions do not define the enantiomorph. The handedness is not resolved at substructure solution. You need to choose the map after density modification that looks like protein. Here's some literature. Bernard Rupp books gives an excellent overview on the different aspects of experimental phasing. Also, the example I'm using in the tutorial is actually the same example that's used in the book. So you could actually go through the 10 pages or so there. There is the improved R factors and the global indicators for X-ray data quality, which has been replaced by the international tables chapter. But this, if you don't have the international tables, is still very good to find the different indicators. It will help you to decide which quality indicators actually to use to find out whether your data have been processed correctly and also whether there is an anomalous signal. Then there's a number of ShellX papers. So this is the ShellX main reference. This is the one which actually has all the mathematical bits about ShellXE's inner workings and is published in ZChrist. Then there is the chain tracing paper, and for Anoda, there's also the Anoda paper. And more material, like the slides of this lecture, and also the tutorial at today evening. I will put up the tutorial there, and there will be a note just directly under the lecture title, linking you to the tutorial. If you want to do the tutorial during this week, you are very welcome to stop by. I'm living in 1.44, or better, send me an email, because I'm not in here every day. I'm in Struby as well. But if you have any problems with the tutorial and you want to do it, basically send me an email and we can meet up and talk about it. And there's also a lot of good material on George's homepage, which has the same first name and then just ShellX. And thank you for your attention.